In this video, I want to show you some counterintuitive examples in C++. For the sake of this description, I created a short example, and I'm gonna allocate a 8 bytes variable as a long int on the heap. And then I'm trying to reinterpret this variable. It's a pointer of a 4 bytes type. So start with an 8 byte type, and I want to reinterpret cast to 4 byte type. So in this way, I can access as an array. So I can access the element 0 and, for instance, put it as 5, and element 1 and put it as 6. And then, like if x is not equals to 0, I want to return this value 42. It's just for the sake of this example. So let's try to compile first without optimization. So with O0. For instance, in GCC, and let's see what we get. In this case, we get 42. Now, if we compile with O2, so with optimization in place, what's going to happen is that it's returning 1. Why is the case? What's happening here? If instead of GCC we try to use Clang, what we get is still 42, which is different from the one that we got before with optimization. Here, compiler implementer can decide what to do as they want, since it's undefined behavior. To understand why it happens, let me introduce first aliasing. Pointer aliasing occurs when a single memory location is accessed through different symbolic names in a program. So it means that the same variable can be accessed in multiple ways. And the compiler cannot perform certain optimization if this rule is in place. Compilers often must be conservative and assume that any two pointers of compatible types might alias. If the compiler cannot prove that two pointers are distinct, it might be forced to reload the values from memory repeatedly instead of keeping them in the register, and this can slow performance. Another optimization that can be prevented is vectorization. So since overlapping memory might alias, the compiler cannot directly substitute certain instructions with the more performance SIMD instructions. Instruction scheduling might be affected as well. So the compiler cannot freely reorder the writes and the reads, so to better utilize all the components of the hardware. If pointers might alias, the reordering might be potentially disruptive for the program, so the program might not be correct anymore. Folks responsible for the standardization process decided that it was too restrictive for a pointer to be allowed to access any other location in memory. So there should be some rule about that. C++ has a rule that is called strict aliasing, and it says if two pointers have unrelated types, the compiler is allowed to assume that they do not refer to the same object. And this is the assumption that enables optimization. According to the standard, if we try to access the store value of a type with a pointer of a type that is not similar to one of the following types, then we have undefined behavior. The cases contemplated by the standard are the dynamic type of the object, a type that is signed or unsigned type corresponding to the dynamic type of the object. For instance, if we convert from int32 to uint32, and third case, if we try to use a pointer to a char, to unsigned char, or std byte type. Now try to compile the program with the following flag fno strict aliasing to see what's going to happen. So in this case, we disable the strict aliasing rule. So we disable the possibility for the compiler to optimize given the fact that we have a strict aliasing in place. And what we notice is that we get the program that we got the result that we got when we had the O0 in place. I hope that you found this information useful, and the next episode we are gonna look at other rules of type conversions in C++ that we need to keep in mind.